Hi everyone, welcome back to our Flownex online training sessions. Today we'll look at the use of boundary values. Now, this may be one of, if not the most important building block in Flownex, and for that matter any system simulation or CFD software. The purpose of boundary values is to tell Flownex what is happening in the part of the system that is not modeled, or else stated, that which is at the boundaries and beyond the section that we are modeling. Without the correct boundary values, the rest of the model will be futile. It will not function properly or give you the wrong results. The component itself you can find under nodes and boundaries. And again, drag drop onto the canvas. And I'll quickly set up the small network we constructed at the end of the previous session using two pipes and a valve, together with the applicable diameter, length, roughness, and valve specification, and also the fluid assignment. At the inlet, we need to tell Flownex if the part of the system we are not modeling contains a high temperature or low temperature fluid, and if the fluid is at a high or low pressure. So it is imperative to specify the temperature and pressure at the inlet. Got that? Okay. Let's look at the outlet boundary value. And I'll first talk about the pressure flow specification. And for this, we'll dig up some theory. A simple representation of the relationship between flow and pressure loss can be imagined using the equation delta P equals FL over D plus K times a half rho V squared, which also equates to delta P equals, again, FL over D plus K multiplied by half times the mass flow squared divided by density and area squared. So with the specified geometry, I can calculate the pressure difference if I know the mass flow, or calculate the mass flow if I know the pressure difference. So I can specify either of the two to calculate the other. But specifying both will be overspecification, and for this reason, Flownex hides the alternative input as soon as I selected the one I want to use. At this point, it is also important to understand the difference between mass flow and mass source, which is our optional input value on the boundary. Mass flow is the value that will be given by a flow meter. So the amount of flow passing through a certain point in my network. A source, on the other hand, is something that is generated or lost at a certain point in the network. So if we want to have a mass flow of, say, 10 through the system, then we need to tell Flownex to discard or release that quantity into the part of the system we are not modeling. So the generated value will be minus 10. If we were to specify a positive value of 10, it would have meant that we are generating fluid at this position into the system. So it would result into a mass flow of negative 10, or opposite the direction of the arrows. And we don't want that. I hope this makes sense to you. So with this in mind, I can specify either a mass source value if I know the system mass flow, or I can specify the measured pressure at the system boundary. For this example, I'll specify a mass source of minus 10. Let's go over to the temperature specification. Do you think it is necessary to specify the temperature at the outlet boundary value? Quickly think about that. Well, actually not. Flownex operates through conservation of mass, momentum, and energy. What this means for the temperature is that the amount of energy is maintained in the direction of flow until heat is added or discarded. So it will maintain its enthalpy value, which is related to temperature, all the way in our network. And if we were to add a temperature value specification at the outlet boundary value, we would only create an energy source on that point, which will have no effect on the network whatsoever. So the bottom line to this is, don't specify the temperature at the outlet boundary value. With this now in place, we can solve the network. And it does so flawlessly. Lastly, let's quickly look at the use of boundary values within the network itself. A boundary value in the middle of our network will induce a source, whether mass by pressure or mass specification, or energy by temperature specification. And I'll quickly illustrate this to you. Let's specify a temperature of 40 degrees C on this position. Upon solving, you'll see that the temperature stays practically 21 degrees C up to the boundary value position, where it changes to 40 as we told it to, and then keep that value up to the outlet. On the node's result, you'll now see that an energy source value is created. Now, this is the amount of heat needed to raise the fluid's temperature from 21 degrees Celsius to 40 degrees Celsius. Note also that although there is a mass flow through the system, there is no mass source result on this node, because no mass source is generated or discarded at this position, as we discussed. By specifying pressure, the resulting effect will create a mass source on the node. This is because Flownex needs to enforce momentum conservation at all times on both sides of the boundary value. In layman's terms, this would be the same as to create two separate networks with the same outlet, inlet, pressure and temperature, but different mass flows. Got that? It might be quite daunting in the beginning, so if you are not fully in control of what I've just explained, you might also consider looking at Flownex's library help manual, which will give a little different perspective on this. Remember that there are always exceptions to the rule, and this convention I gave you is only a starting guideline, but it will work in 99% of all cases. And that concludes our session on boundary values. In the next session, we'll look at pumps and its selection using the fixed mass flow functionality. So until then, have a wonderful Flownex time.